Okay, so this is WebAssign 9C and question number 5. So it says, a long straight metal rod has a radius of 5.5 centimeters and a charge per unit length of 31.8 nanocoulombs per meter. Find the electric field at the following distances from the axis of the rod, where distances are measured perpendicular to the rod's axis. Okay, so A is, it says, so for all of these, we're going to find the electric field at the following distances. So for letter A, it says 2 centimeters. So we know that R is 5.5 centimeters. And so it's important to note here, where some kids get tripped up, is that because the distance inside the conductor, it's shorter than like the radius of it, the electric field is 0. And for all conductors, a big part of this problem will probably be that the electric field is 0 in all conductors when the distance is smaller than the radius of the conductor. Anything outside, it has an electric field, but inside it doesn't. So therefore, this answer will be 0. E equals 0. And the magnitude, we can just put magnitude is 0. So for direction, it has no direction, it's 0. So just remember that. So B, we see that, okay, there's 17 centimeters. So for this part, it's important to remember that electric field, this is what we found out in I think one of the labs that we did too, is that it's important to remember that the electric field is directly proportional to the charge density and inversely proportional to the radius of whatever surface, so of the Gaussian surface. So for this one, it'd be a rod, so our Gaussian surface is just like a cylinder basically. So it's that gives us electric field is directly proportional to the charge density, so E is equal to lambda, charge density, and it's inversely proportional to the radius of the Gaussian surface, so we use 2 pi epsilon naught r, so that's our starting equation, and we can just plug in, we know pi, we know lambda, we know r, so yeah, we know everything, we can solve this. So E is equal to 31, lambda, it said 31.8 times 10 to the negative 9th coulombs per meter. It said that in the question. Actually, I believe it gives it to you in nanocoulombs, nanocoulomb per meter. So you get the nanocoulombs just means times 10 to the negative 9th. So whenever you see that, that's where some kids get tripped up. So just times 10 to the negative 9th and nanocoulombs. So that turns into coulombs. Times 2 pi, epsilon is a constant, 854 times 10 to the negative 12 force per meter, times 0.17 meters. Pretty sure it gives it to you in centimeters, don't forget to convert that. 0.17 gives it to you. So the final electric field we get is 3.36 times 10 to the third newtons per coulomb. So that's the electric field at that radius at 17 centimeters. And then C says 170 centimeters, so okay, getting bigger. So we can just use the same equation we used in the first one, because the same rule applies here. Electric field is directly proportional to the charge density and inversely proportional to radius of the surface. So E equal to lambda over 2 pi epsilon naught r. And we use mostly say r is the only thing that changes here, so 31.8 times 10 to the negative 9th coulomb per meter, all over 2 pi epsilon naught times the radius, times 1.7 meters here. And that gives us a final electric field of 3.36 times 10 to the second newtons per coulombs. So this was a tougher problem. This is more like concepts too, and like applying like some math too with it. So just basically, the thing I learned from this problem was that any distance they give you r inside of the conductor, electric field is always 0 inside a conductor. So, and then outside of it, there's an electric field. And also, something that we use in this was that I learned that the electric field is directly proportional to the charge density and inversely proportional to radius of the surface. So yeah.